it's really an interesting model, and they appear in many fields of science. So people already know that the idea came from Turing in his paper article 1952. There's a very fascinating idea proposed by Turing. Basically, you realize in a homogeneous medium, spatially heterogeneous disputed pattern can be produced from chemical reaction of two substances with different diffusivity. There's an interesting article by Kondo and Asai, which published in the Nature. Basically, in their laboratory, they study the reaction diffusion wave on the skin of some tropical fish, and there are patterns on the skin of such fish. So they look at such patterns, and in their observation, they find that, okay, strip pattern appear on the skin of the fish, and such pattern changes during the growth of the fish, and they use reaction diffusion system to simulate such patterns. So that's the result of a numerical simulation, and they find that actually they look like quite similar, and it seems that they can use reaction diffusion equations to predict the conformation of such patterns. And so such strip patterns, people would thought about it's some kind of tuning patterns. But we are also interested in particle-like structure. They are also commonly observed in many systems. And in reaction diffusion system, such particle-like structure are referred to as dissipative soliton. So for instance, you could have, this is two-dimensional pulse, okay? And you could have two or many of them. Also, such dissipative soliton usually move depending on the system parameters and the initial conditions. Such wave may stay at rest or propagate with a dynamically stabilized velocity. So could be a standing wave, looks like a pattern, but in most of the time, they move with some constant velocity. This is so-called time wave, and but the structure of this pulse or particle actually is a local structure. So we have seen several pictures that pulse self-organized patterns or waves. The profile of such pulse basically stay very close to a trivial background, except for one or several localized spatial regions. Such solutions if we study differential equations, because they are far away from a homogeneous equilibrium, so they are not the tuning patterns, because it's very difficult to find such solutions near the neighborhood induced by the tuning stability. So they are usually far away from a homogeneous equilibrium. And if you want to use, mathematically, if you want to use bifurcation method, it's difficult to prove that such existence results. So in today's talk, I like to look at so-called FitzHugh-Nagumo equations. This is a system. Basically, it can be viewed as a system of an activator and inhibitor system. So this nonlinearity f is a cubic polynomial. So so let me just give the idea of this, the picture of the f. This is a cubic polynomial, and here we call it beta. Here is 1. So f of u basically is u times 1 minus u times u minus beta. And the beta is a number between 0 and 1/2. And therefore, if you look at this function, 0 is a rest state. And assuming here there's a so-called excitable state. Okay, so if you only have the first equation without v, okay, so this is called Nagumo equation, and this is tells you there are 3 equilibrium with 1 excitable state. So this is so-called excitable system. But then when you have inhibitor V added to this system, then there are many, many more interesting phenomena can be found, and people already find such solution numerically. However, this is a system, and then mathematically, it's not a monotone system. Therefore, certain technique like maxima principle or comparison argument cannot be applied directly to the system. Although single equation is okay, however, it does seem to be easy to find pulse solution or triangle waves. Okay, in certain well, there are some people use singular perturbation to work on that. But in general, if you want to study more general range of parameters, then we try to see if we can use variational method to study such kind of questions. So assuming that you have a solution in this form, okay, so this is a function moving with constant speed c and keep the same profile at all the time, and so this is a well-known solution, so-called triangle wave. And in particular, if the speed is 0, then it's a standing one. Well, actually, in the history, this is a so-called FitzHugh-Nagumo system. So the difference is on the second equation, there's no diffusivity on V. Okay, that's a simplified model for Hodgkin-Huxley system to describe the wave propagation of for the in the axon of squid. And so that's a quite well-known result, and so Hodgkin and Huxley actually did a very good contribution for this. People try to understand the nerve impulse. So basically, it's generated by a finite excitation. So mathematically, if we want to prove the existence, then it's not an easy work. However, it's already been done by singular perturbation method when epsilon is sufficiently small. But when the second equation also include diffusion, then so far singular perturbation method still has some difficulty, cannot be worked out yet. So I'm trying to take this problem to see how do we do it using variational method. So I think this is a very good opportunity to talk people in the institute and see if we can find a good application in physiology or other field. Okay, so the first one, I assume, okay, so for the second equation, the nuclei is U minus gamma V equals 0. That's the nuclei for the second equation. And then the first equation basically is V equals F of U. That's the nuclei. Okay, so if you compare such two equations, it tells you one is just the curve F of U. So if you take this is U, this is V coordinates. And then the other, you get V equals 1 over gamma times U. Depending on the value of gamma, so you have a straight line. Basically, for small gamma, there is only one equilibrium because this is only the intersect point. But if you increase the value of gamma, you could get 2 or 3 equilibrium. Okay, so when there is only one equilibrium, this is so-called a monostable case, and the other is so-called bistable when you have 3 equilibrium. But today, I'm aiming at the case monostable case. Okay, so the first result I want to tell about is the standing wave. So what we have proved is there exists gamma hat and the D hat, such that if gamma is less than gamma hat and the D is less than D hat, there is a standing pulse solution. Okay.
So what was D?
Oh, D, right, okay. D is diffusion. Okay, so
D is the diffusion coefficient of D, is it?
right, so I wrote this way. Ut minus Laplace of U equals F of U minus V. However, I put the 1 over D here.
Okay.
Yeah. actually for the standing wave, we can relax a little bit, and we can just put a D in front of diffusion. Okay, yeah. But also, I'm working on the trine waves, and it has more restriction on that. Okay, so the profile standing wave is an even function, and in fact, if you look at the numerical result, that's a profile of standing pulse. So it's an even function, and this U change sign once, and the V stays positive. Okay, and so on the half line, V is monotone decreasing. And actually, we prove such results. So we give a very precise description of the profile of such localized pulse. Okay, and we are also interested in the trine wave, and we just assume C to be positive. Okay, so the second result is for the trine pulse. Again, we can find some speed C so that the FitzHugh-Nagumo system persists a trine pulse solution, and both function U and V are exponentially decayed. Okay, so the profile of a trine pulse actually break down the symmetry. Okay, it has to be, otherwise it won't move. So, so that's difference between standing and the driving pulse. Here.
Sorry, can I ask a question? The first theorem said that under certain conditions you had a steady state solution.
Mm-hmm.
And now the conditions look very similar. You say there is a sum for some positive C. So for certain data you have both the steady state solution and the traveling pulse.
Right.
But then you expect the velocity to be fixed.
Velocity depending on gamma and the D, but yeah.
Okay, so then you have basically two types of solutions.
Right.
Okay.
Yeah. However, in different parameter region, the standing one is stable. Okay, and in different parameter region, this driving pulse is stable, and the standing one loses stability. Okay. Yeah, thanks for the question. Okay, so here, okay, actually, this is U component. Actually, it's very close to zero. However, it's slightly negative, but it cannot be shown numerically. And this is part of V. So V actually push this trine wave move in this direction. Okay, so in the rest of time, I will be more concentrated on the trine one. And of course, the proof are not the same. However, there are more technique involved in showing the existence of trine wave. Therefore, I will go through most of time, most of part, just on the trine wave. But in case if we have time, or we can have some discussion for the standing wave, if people also like to know more about that, I'd be glad to talk about. So here, well, for scalar reaction diffusion equation, so if you have a single equation, there are many, many results for this reaction diffusion equation, because in this case, you have a large method can be used. You can use shooting method if you study the primary wave, because it's just an ordinary differential equation. You can look at the phase plane, or you can use the maxima principle and to study such waves. And also, if you like to use variation method, then you can look at the result of Lucia, Moratov, and Novaga. Here, I like to use this scalar equation to explain certain technique involved in variation method. And since it's simpler, so I use them as an example to show some basic technique involved. Okay, so what you want to do is to study this functional. And C is unknown. So firstly, you have to determine C, that's the speed. And once you can determine the speed C, then you try to find a critical point, in particular a minimize of this I of C. Okay, it will give you a triune wave. Okay, so here, let's just look at this f of u, the same here. This is so-called Nagumo equation. And so capital F is just mass of integral small f. Here, you can immediately find that when you want to find the minimizer, even you already know C, okay, even assume you know C. But now, if you look at the minimizer of this function, okay, if you pick out a function W, and you take a translation of W, okay, this is autonomous equation. Therefore, if you have a solution and you take a translation, it's also a solution, right? However, if you compare, if I call this energy, then if you compare the energy, it's easy to find such a relation. It tells you if this quantity is positive, then the minimizer should be what? Should be 0, because you can take A to be negative infinity, right? But on the other hand, if this quantity is negative, then what happens? Then you would get minus infinity as A goes to plus infinity. Okay, therefore, if you just look at the minimize of this function, you will have such kind of difficulty because you can shift the function through the coordinates. Therefore, what it can do is seek a minimizer under the constraint, okay, under this constraint. Once you impose this constraint, then the freedom of shifting disappears. Therefore, there's a minimizer. Okay, so what they did was, when this quantity, you pick any C, okay? Pick any C. As long as you can find a function U of C, which is a minimizer of IC. So as long as you can prove that a minimizer UC of IC is non-positive, then you can find a triune wave, because you can just rescaling U hat and C hat, you get a triune wave. Okay, and the C hat is the speed. So here, although you don't know the speed C, but once you can get this result, you find a triune wave. And the speed should be C hat. Okay, that's a rescaling. Okay. So basically, you can think about when you minimize something under a constraint, then you would get something so-called Lagrange multiplier. Okay, so this is related to the Lagrange multiplier. Okay, so, well, usually when we study trine wave, we use the ansatz x minus ct. However, there's a different ansatz proposed by Heinz. So he used such kind of ansatz. And then a function satisfies this equation represent a trine wave solution. Okay. And so when you use a different ansatz as proposed by Heinz, well, you study this actually Heinz study this functional. Okay. No, he studied, well, simple one, this functional, subject to the constraint, this one. Okay. And again, with this constraint, there must be a Lagrange multiplier. But in this approach, the Lagrange multiplier is 1 over c squared. And the absolute value of c gives the wave speed. Okay. So we basically follow the ansatz proposed by Heinz. So we want to study the homoclinic solution of this system. Okay. So then, okay, so we have to show the solution we obtain actually is a trine pulse. Okay, I will talk to you later. Okay, so we know the second equation is a linear equation, so we can solve the second equation, V, in terms of U, using green function. So the green function can be write down explicitly. And okay, so we look at the second equation, and so we have the characteristic equation with two roots. One is positive, one is negative. I call it R1 and R2. Okay, so when you use the ansatz proposed by Heinz, you can study functional on the same weighted space. Okay, so the weight is EX instead of ECX. Okay. Okay, so I call, so given U on the second equation, so the second equation is dd dt, but now I call it, I simply have c squared vxx minus c squared vx equals u minus gamma v. Okay, so I'm just studying the primary waves. So depending on C, okay, so depending on C, we have a different green function. However, for any C, once we have u, we solve this equation in terms of v. So I can move this term to the left-hand side and solve this equation through the convolution of u with against the green function. I get a v anyway. And I call this v LCU. And this LC actually is a self-joint. Okay, so for any u in H1 with weighted H1, then you can find V. I simply call LCU. Then, so actually we study the functional JC on the weighted Sobolev space H1. Okay, this, of course, is a Hilbert space. And now I have 3 terms. Okay, so firstly, I have this wave. And the first one came from 1 over d, so, but you have c squared, so this is the gradient term. And the third term came from small f, that's f of u. But remember, this is minus v here, give us what? So if you look at this term, this should be 1/2 u times LCU, because once you replace v by LCU, this is a differential integral equation, okay? Of course, here I should also replace this by minus d. Okay, if I don't want d put here, I can have dc squared uxx minus ux. That. Okay, and since this LCU is self-adjoint, so there's a variation structure associated with that. Okay, so this is a non-local term. Well, again, we can shift the function as we mentioned before, and with such properties. And therefore, we also want to impose the same condition as before. Okay, so firstly, let me just mention some good property of this function space. And actually, we have some kind of Poincare type inequality. And also, we can get some kind of Sobolev embedding like this. Therefore, you can easily to show that actually, if you have a function u, you take the operator LC on u, you have such kind of estimates. And so, therefore, you can take this norm, okay, due to the Poincare inequality as an equivalent norm for H1, okay, weighted H1. Okay, so then it's not difficult to show such estimates. In particular, I'd like to mention that this term, non-local term, u LCU, with the weight, this is like an inner product, is always non-negative for any u you pick it in the function space we are working on. And so we impose the same constraint on that due to the translation. Okay, then we want to find a minimizer. The first thing we like to find the speed of C. Although we already know this C can be found through Lagrange multiplier. However, they were dealing with single equation, and we are dealing with a system or one equation with non-local term. Therefore, it would be difficult to keep this if we rely on the Lagrange multiplier. So we try to avoid Lagrange multiplier. Let's see what we can do. Okay, firstly, we know C cannot be too large. Okay, this is not so difficult because if C is too large, okay, you can find such kind of estimates. Okay, so then this is positive. Okay, so let me just explain that. So for capital F, the graph looks like this. And therefore, you can find parabola underneath to support this. Okay. This capital F. That's the reason that we can do this estimates. Okay, and so therefore, when C is big, the infima is always positive. Okay, and also we are going to show that for small c, the infima is negative, and then we want to use continuity argument to find a c such that the infima is 0, and that one gives us the speed of train wave. Okay. Okay, so remember, we can pick a different answers. One is by Lucia, Morakov, Gova. One is by Heinz, but they are related. However, we can just easy to calculate that. Basically, one is with a functional with weight depending on C. The other, you can use the same weighted space. And but now let's see. If we use this back to this one, there's a C in front. And when C goes to 0, this goes to 1. Okay, so this is look like, when C goes to 0, it looks like a standing wave. Okay, and but the standing wave, actually, we can show that the energy is negative. Therefore, for small c, this quantity is negative. Okay. What we can do, actually, just use a test function. You just say, okay, I take a piecewise linear function, very simple, and I just show that with appropriate choice of A and B, I can show that this quantity is negative. Therefore, you know, the infima of J of C, when C is sufficiently small, it should be negative. All right. Then what we want to do is to show some continuity for this function of J. Okay, so we want to show some continuity of this function J depending on C, and therefore the infima we call script J of C should be also continuous. Okay, now then we already know for small c is negative, for large c is positive, therefore there's at least 1 of c. The infima is 0, and that's the candidate of the speed, traveling speed. Okay, so that's just some standard analysis. You can show such continuity. Firstly, we want to show the continuity depending on L or L tilde. Okay, because we have to translate to L tilde just because if you choose L instead of L tilde, the advantage is working on the same space with the weight EX. However, the functional actually is not continuous at 0. So therefore, we have to go back to the other answers. But that's just a technical consideration. Okay, so once we show this inf actually is continuous function, therefore we can always pick out a C0 as the speed. Okay. Well,
Excuse me, do you also show uniqueness?
no, it's difficult.
So you have one.
Yeah, and it may not be unique. Yeah. Okay, so then with such speed C0, you look at this functional because the infima is 0, and you can find a minimizer as a limit of minimizing sequence. And then this U0 is a triangle wave in the sense that due to the Poincare type inequality, we know the solution decay to 0 at infinity. However, if you look at this weight, EX, at the minus infinity, this weight is very, very light. Okay, very, very light. So you don't know this U0 has to go to 0 or even bounded. Okay, but of course we can show it's bounded. However, it's not so easy to deal with the asymptotic behavior of such triangle wave near minus infinity when you use a variational method due to this weighted function space. Okay. Well, in the scalar case, the maxima principle usually can provide some help to complete this task. All right, so now what can we do? Well, so we introduce some topological constraint. Okay, so we say we want to find admissible function in the class minus plus minus. Okay, so this is typical one. Minus here, plus here, minus here. However, you could have 0 on some interval which is identical to 0. Okay, and moreover, you can, well, basically we can pick up 2 points, x1 and x2, okay? However, the choice of such 2 points is not necessarily unique, okay? For instance, you can pick this case, then actually the function is positive function or non-negative function. And if you pick this case, then actually it's non-positive on the real line. Okay, so both of them are allowed in this class. And I would say this is the degenerate case, but we want to show the solution is not in the degenerate case. Okay. But then, again, once you impose this topological constraint, you want to solve the problem we have seen. However, you have to pay more price to work on analysis. Okay. So we want to show the solution. Actually, if you don't impose the constraint, then then the minimizer satisfies the Euler-Lagrange equation. Okay. However, once you impose such a topological constraint, what happened is you could have solution which is identical to 0. And in that part, this is due to the constraint. So you could have some kind of Lagrange multiplier, which means that part of function u0 does not satisfy Euler-Lagrange equation. Okay, you want to you are aiming at the Lagrange equation, Euler-Lagrange equation to be this one. However, if it's identical to 0 on some interval, then on their part, it's definitely not. Okay, so what we try to do is to rule out such possibility by using some kind of surgery. We generate a new function and to show that this inequality. However, this cannot be true because you already know this is a global minimizer. Okay, with fixed C0, you know the inf is 0, and you already showed this quantity is 0, and this one has to be negative, then it cannot be true. That means the global minimizer of u0 cannot be identical to 0 on some interval. Of course, that's the idea. However, you want to show that there are lots of technique we have to face. Okay. Firstly, the difficult part is the non-local term, because the non-local term is really, really hard to control the behavior. When you even you change something locally, but you have to know what happened on the whole real line. Therefore, what we can do is use this formula. Okay, so you just want to compare the new function and the original u0. What's the non-local term, the difference between them? It turns out it's this. Okay, then what we can do is, if we take a small surgery, that means you just take a very little perturbation from u0. This quantity should be very small, and by continuity, this quantity should be about twice of LC u0. Okay, so then you can do some calculation. Okay, the good thing is, in most of the time, you can do some surgery, although it's not easy, but if you can find some certain surgery inside a finite interval, then the non-local term can be calculated within the same interval AB, right? Because they are only difference in a finite interval, and therefore makes this calculation easier. Even though the behavior under the sign of this term near infinity can differ from those of that. This is very, very hard to control. But once we did this on a finite interval, on a compact set, we don't need to worry about this. Okay, well, so far we already get a minimizer. However, we know that it's in the H1 with the weight. However, so it tells you u0 is continuous function, but not necessarily C1. Of course, it's not necessary to satisfy Euler-Lagrange equation. Therefore, we have some difficult to deal with this u0. So what we can do is we use this Kohler lemma. Okay, so it tells you that, so you suppose you have a solution, looks like this. which is identical to 0, something like that. Or you could have something look like this. Okay, either way, here is identical to 0, one interval like this. Okay, then one thing you can show is the derivative has to be 0 here and here. Okay, so this is the so-called lemma to make sure that there's no sharp corner at the end of the interval. Okay, so once you get this, you already know U0 is C1 function. Okay, although it's not C2 yet, but the C1 function helps a lot. Okay, I probably skipped the idea of the proof of lemma. Anyway, you have to compare certain. So what you can do is so here, suppose they are not continuous. So the derivative, the right-hand derivative is not equal to the left one. Then what you can do is you just take the average, something like this. But you keep this interval very small. Then you can show that eventually the energy decrease. Okay, that's the idea. All right, the next thing will helps us a lot is to find the sign of V. Well, we already see numerical picture that the V stay positive. However, we have to show that. Okay, so here, once we already know U0 is C1, so we can look at a function called psi. This function is U0 plus some number alpha times V0. Okay, so this is a C1 function, and but also it could be C2 function at the other point if it's not identical to 0. Okay, so this function actually with appropriate choice of alpha. Okay, this alpha actually depending on the decay rate of U and V, U0 or V0. So if you pick a good alpha, then you can study this function phi. And this phi satisfies certain differential inequality, which allow us to use the maxima principle. And also, you already know U is in C1, so V is U0 is C1, therefore V0 is C3. Okay, so automatically, second equation, this one you can use maxima principle to work on that. You can also use maxima principle work on this. Okay, so you have two equations you can use, and then with certain analysis, like a maxima principle and half boundary lemma, you can show that actually this function phi has to be positive everywhere. And then the next step, you can show that the V0 is a positive function. Okay, then you already know, once you know okay, here, if you know V is positive, then this function is positive. Then you can look at this integral and to find out the sign of this one. Okay, so once you get the property of V0 being positive, then you can do more things along certain surgeries. Okay, so that's also an important ingredient in showing the minimizer satisfies the Euler-Lagrange equation. Okay, so once we know the sign of V0, then we can use certain surgery to show, for instance, the maxima of U0 is between beta 1 and 1. Okay, beta 1 is this point, 1 is here, beta 1 is this point. Okay. And then the next thing, although you already know U is C1, but you really don't want this happen. So you want to show that actually there's no interval on which U0 is identical to 0. Okay. Once you get this part done, then you are sure that this U0 sets the Euler Lagrange equation. Okay, so it will be a triangle wave. Okay. Well, certainly there are some difficulties because, for instance, suppose you have a function look like this. Say, let's put it this way. Okay, suppose look like this. Okay, then this one, what you can do is say, okay, I perturb this function a little bit. I choose a interval a, b, and just take it down a little bit. Okay. Then this function is still in the class minus plus minus. Okay. This is okay. So for instance, I can pick this new function like this. Okay. Then you can calculate the energy decrease. Therefore, here cannot be identical to 0. But you could have something different. Look like this. Okay, here the same trick won't work because if you perturb a little bit here, then it's in the class minus plus minus plus minus out of the class. Okay. What?
Can you make it positive?
No, positive won't work. You make positive, then you increase the energy, not decrease the energy. Okay, yeah. Okay, so then you have to use a different technique. For instance, you shift this a little bit and try to show the energy is negative. Okay. Okay, so I think I probably will end at 12:10, okay? Well, actually, let me just put a remark. Although I say, okay, it could be identical 0 on an interval, but in the worst case, you could have accumulation point that you have an infinite number of interval that which is identical to 0, but the interval getting smaller and smaller, you get accumulation point. Again, you can use more analysis to rule out such possibility. But what I'm saying is some arguments are tedious, but you have to face two. Okay, now I think this is the last slide. So what you know is the function now, U0, okay, cannot be identical to 0, so it's negative here, then positive here, then it cannot be identical to 0. But there's another possibility is like this. Okay, and it can be oscillated infinite times. This is still in the class. Right? And this happened, then we cannot conclude that the solution is a pulse. Okay? Therefore, here is the argument we used. So firstly, we define this function W1. Pick any point x1, x2. Okay, So this is this quantity. But we already have okay, this function, but we already know both u and v are in at least C2. Actually, they are in C infinity now. And we can get a uniform bonds on u together all its derivatives. Therefore, this quantity actually is independent of choice of x1 and x2. So this quantity is uniformly bounded for any choice. Okay? And similar, you can look at this function, okay, which is this, but similar, this is also uniform bounded. Therefore, you took the difference of them, which is equal to this integral. Now here is the point. If u is, sorry, u is oscillate, but it stays non-negative. So then, if we look at this picture, this line, u over gamma is strictly above f of u, right? Because u stay positive. If u become negative, then, well, it won't work. But if u is positive, then you stay. So this quantity, u naught over gamma minus f of u naught, is greater than some constant n times u naught, right? Because from this picture, you can get that. All right. Therefore, from here, this is some constant, so you get this. That means u naught actually is in L1 on this interval. Therefore, it has to be decayed. Okay? Because if u does not change sign, it has to be decayed. But actually, once it becomes negative somewhere, then because it's in the class minus plus minus, so it cannot go up again. Okay, in force to be negative for all this interval. Okay, all right. So this tells us that we actually get a pulse, and but then we probably need 10 more pages to show that actually the solution actually just look like the numerical result we got. Yeah, like this. So actually, with more analysis, we can show that this pulse solution actually has to be negative here and here, and there's only one pulse. Okay, but it requires more analysis. But I think I already talked about the main idea for using variation method to show such solutions. Thank you for your attention.
Thank you very much. Any questions, comments?
You think there can be multiple traveling pulses?
Well, you are thinking maybe you can use a different class, maybe say minus plus minus plus minus, but you know, you can use that class. However, you have to find a way to show it's really in that class is non-degenerate. It could be degenerate. If it degenerate, it's still one pulse. Yeah, that's a difficult.
Well, if not, thank you again.
Thanks.